Hello everyone and welcome to a new recitation. Today we will be solving problems related to problem set number 5. So let me begin. Okay, reading the problem. Number 1, it says determine phi Rn, the capacity, in accordance to LRFD and ASD for the connection shown below based on both limit states bearing type connection. The standard holes are given to us, and it is mentioned that the plates or what we have in here, the connection is made of steel 275 with the yielding stress of 275 megapascal and F ultimate equal to 430 megapascal. Now, as we can see here, this is our connection. We have two thick plates of 8 millimeters that are connected together by bolts as shown. We have in total 9 bolts, and we have the spacing between all the bolts. And in part A, it tells us to find, or it is given to us actually in part A, that the bolts are a size of M20 and they are grade 8.8 with the threads excluded from the shearing plane. And let me mention this also, we have a force that is applied on both of the plates as shown in here. So we would like to find the capacity based on the bolt limit states. So beginning with part A, considering that we have size M20, we can calculate the area of each bolt. The area would be pi r squared. In this case, it would be pi multiplied by 10 to the power of 2, and that will give us 314. The F ultimate is basically 800 megapascal because the grade is 8.8. So we are taking the first value in here, 8 multiplied by 100, 800 megapascal. And the Fy for bolt is the second value in here. We multiply it by 800. And that's how we get Fy, and it is equal to 640 megapascal. Now, considering the shear capacity of each of the bolts that we have, based on the provided information, we can calculate it from Rn is equal to Fnv, the net shear stress capacity, and multiplied by the area of each bolt. So first of all, since the problem in part A, it says that the threads are excluded from the shear plane, therefore I would multiply 0.625 by 0.9, which is something you can recall, 0.563, multiplied by F ultimate. Now that's again this number or this value because the threads are excluded from the shear plane, multiplied by F ultimate, and lastly multiplied by the area of each bolt. So the area of each bolt is 314, and we divide by 1,000 because I would like to convert from newtons to kilonewtons. Now, multiplying all of these and calculating that, we would get the capacity of each bolt in shear is equal to 141.5 kilonewtons. Now, also, we have to consider that we might have bearing for the bolts that we have. So, for instance, the bolts, if we consider in here, one of the bolts, or let's take 2 of them. So, for example, the outer bolt in here might be tearing out and touching the other bolt, and that is a problem that we do not want. Or we might have an excessive deformation where the bolt becomes over here. Beside that, the bolt at the edge, for example, might go out. We might have complete tear out and the bolt might go out. Beside that, if we consider the bolts, the inner bolts, this bolt, for instance, might go to the direction of, as shown in the arrow, and it might reach the other bolt in here. So we want to consider the capacity of these cases. So if we take a look at the bearing of outer bolts, I will be using this equation in order to calculate that capacity, and I will be considering the plates in for this equation. So in this equation, it says the capacity or Rn is equal to 1.2 multiplied by LC. LC is the clear distance. multiplied by the thickness of the plate, and lastly, F ultimate of the plate. I repeat all of this for the plate. So if we consider, for instance, the outer bolts, we have the clear distance LC, or sorry, not only the outer bolts, we might have, yes, so the clear distance in here, if we consider this part, from the edge of the outer edge of the bolt to the edge of the plate is called the clear distance. This is LC. Now I can say that this is LC1, and in order to calculate LC1, basically in the problem you are given from the center of the bolt to the edge that this is equal to 50 millimeters. Now we would like to consider the length LC1, so therefore I say 50 minus 22 divided by 2. Notice that 22 is the diameter of the hole, not the bolt, but the hole. So I'm giving extra 2 millimeters to the size of the bolt in here as a whole, and I divide by 2 because it was originally given that it is from the center. So I'm subtracting half whole diameter. And therefore LC1 would be equal to 39 millimeters. Now there's another possibility that the outer bolt would go to the other bolt that is beside it. So therefore I would have to calculate LC2 value. Now how would I calculate it? Again, the same logic. Before we were given that the distance from the center of a bolt to the other one is 75 millimeters. Now as you can see here, I need from the outer edge to the outer edge of the other bolt. Therefore I subtract one whole diameter. So it becomes 75 minus 22, and that would give us 53 millimeters. Now, since I have the LC, I need to substitute in this equation, I have to consider one of these values, either 39 millimeters or 53 millimeters. Now, in our condition, since both plates are having the same thickness, I will choose the lowest LC value. Why? Because it is more critical. And substituting that LC value, so it becomes, and substituting the other values, we have 1.2 multiplied by 39, that's LC, lowest one, multiplied by thickness of lowest plate, which is 8 millimeter in both cases. So again, in the problem, it says that 8 millimeters is the thickness of the plates. And lastly, multiplied by F ultimate for the plate, 430 megapascal. Now from here, we get the value for Rn, the capacity based on the bearing of outer bolts is equal to 161 kilonewtons from this equation. Now I have to consider also the other capacity for the inner bolts. So we might have excessive deformation, and that is something we do not want. Therefore, I have to consider the equation in here. Rn is equal to 2.4 multiplied by the diameter of the bolt, multiplied by the thickness of the plate, and lastly multiplied by F ultimate for the plate. So substituting the values we have 2.4 multiplied by 20. 20 is, again, that's the size of the bolt, multiplied by 8, the thickness of the plate, and lastly 430 is the F ultimate for the plate. From here, as you can see, I have three capacities, 141, and I have 161 and 165. So I can create a table. I can say that, okay, this is the capacity for the bolt shear, the bearing of outer bolts, bearing of inner bolts. And I have each capacity as shown. Now, before we proceed, okay, so if we actually consider which one is going to be my capacity, obviously it will be the minimum value. So bolts and shear shows that it is the minimum or the least one with 141.5, and therefore I will say that, okay, this is going to be the capacity of all my bolts. And I will take phi Rn, or the factored capacity, 0.75. I will multiply it by a capacity of one bolt, 141.5, and lastly multiply it by 9 bolts, because in the problem I have 9 bolts as shown in here. Erase everything. Yeah, so as you can see, I have 9 bolts, and therefore I'm multiplying the capacity of 1 bolt by 9. And from there, I get the capacity of the whole connection as 955.13 kilonewtons. And if you would like to calculate it based on ASD, instead of multiplying by 0.75, I divide by 2. And again, you get the capacity according to ASD, 636.75 kilonewtons. Now moving on to part B. In part B of the question, it says, if the size of the bolts is 24 millimeters, M24 in size, and we have the grade 8.8, again the same, the threads excluded from the shear plane, calculate the capacity of the connection. So the shearing capacity of each bolt, again, the same as we did before. Rn is going to be equal to FNV multiplied by the area of bolt. So in here we have, since threads are excluded, I'm using this value, 0.563. That's what you would obtain from multiplying those two numbers, and multiplied by F ultimate. Now lastly, I'm multiplying by the area of 1 bolt. So obviously 12 is half of 24, that's the radius. And I divide by 1,000 to convert from newtons to kilonewtons. Now from here, after calculating this, you would obtain the shearing capacity of each bolt to be equal to 203.57 kilonewtons. Now we move on to the other part. We want to check the bearing of outer bolts. So based on this equation again, Rn is equal to 1.2 Lc by the thickness by F ultimate. And all these are related to the plate. Now, considering the LC value, I have to consider that I have the outer edge of the outer bolt in here. That's 1 LC. The LC value, same logic as we did before. It will be, however, 50 minus 28 divided by 2, because now notice in here, 28 is the whole diameter. And since the bolts I have are M24, I'm saying 24 plus 4 is actually the whole diameter. That's how I got my 28. Of course, you divide by 2 because the distance was given from the center of the bolt originally as 50 millimeters. So I'm subtracting half whole diameter. Now, on the other hand, so this is LC1. On the other hand, I would like to calculate the distance between two bolts, the outer one and the inner one. So LC in this case would be 75 minus 24. So actually, this is not supposed to be 24. It is supposed to be 28. However, in any case, LC1 is going to be, so this is LC2. In any case, LC1 is going to be the least one. And I will substitute it in my equation in here. So 1.2 multiplied by 36, LC1 multiplied by 8, the thickness of one plate, and lastly 430, that's the F ultimate. Now from here, I get the bearing capacity equal to 148.6 kilonewtons. So that's the equation for the tear out. Now for the bearing of inner bolts, I have to consider this equation. And based on this equation, basically substitute 2.4 by the diameter of one bolt, 24 millimeters, multiplied by 8 thickness of plate, and lastly F ultimate. Again, I get another capacity as shown. Now, if we compare between our findings, we have the shearing capacity, 203, 148.6, and 198. Now, obviously, the bearing of outer bolts is the least one. So you would say, basically, in order to find the capacity of the whole connection, I would multiply this value by 9. However, this is wrong. You should not do that. You do it only in case that you found that the shearing capacity of each bolt is the lowest. But since the bearing is our case, I have to consider each separately. So what does that mean? It means that I will take this value in here, this value over here as well, and I will consider how many bolts are under these conditions. So if you look at the outer bolts, In our problem, you have 3 bolts that are outer for the plate that is below in here for this plate, and you have outer bolts that are over here, and they are outer for this plate. So in total, I have 6 bolts, and the inner bolts are 3. So if we go back again, in order to calculate the capacity, I'm multiplying 6 by 148.6 because I had 6 outer bolts, plus 3, that's the inner, multiplied by the inner bolts capacity. And from here, of course, I multiply by 0.75 in accordance with LRFD, and I get the capacity as 1014.5. Lastly, in order to find it in accordance with ASD, the same logic, however, we divide by 2 instead of multiplying by 0.75. And also we get the capacity according to ASD. And here we can see summary for all the findings we have. Now moving on to the last part of this problem, part C. In this part it says if your bolts have a size of M22, or they are M22 bolts, grade 8.8 again. However, this time the threads are included in the shear plane. So what would be the capacity of your connection? Now I'm sorry for this. Yeah, so all good actually. Now calculating the shearing capacity again as we did before. Now notice in calculating F and V, I have used 0.45. Why is that? 0.45 because the threads are included this time. Therefore, I'm multiplying 0.45 by F ultimate 800, F ultimate for the bolts, multiplied by the area of each bolt, 380, and I'm dividing by 1,000 for conversion. And from there, I get the capacity in shearing for bolts to be equal 136.8 kilonewtons. Now, considering the bearing of outer bolts, calculating LC values, I have this LC value. It appears that it is 38. Of course, I'm considering the hole diameter, not the bolt diameter, in calculating LC. So this is 38 millimeters, and the one in here would be 53 millimeters. So obviously, this one is lowest. I'm going to substitute it in my equation, and I will consider the characteristics of the plates as the thickness and F ultimate. From here, I get the capacity to be equal 156.86 kilonewtons. Lastly, the bearing of inner bolts. So from here, 2.4 multiplied by the diameter of a bolt, thickness of a plate, and F ultimate, and you get the capacity based on that. Now, as you can see from here, that's my lowest capacity. And from there, you can basically, of course, have everything organized, and you can find the capacity of the connection based on this condition C to be equal to 136.85 multiplied by 9 bolts and multiplied by 0.75 according to LRFD. From there, you get 923. Lastly, if you'd like to calculate in accordance with ASD, you divide the thing, what you have calculated, by 2. And from here, you get the capacity with ASD to be 615.82 kilonewtons. Now, moving on to the second problem we have, it says for the connection shown below, determine the number of M24 grade 8.8 bolts required for a bearing type connection. And it says that PU is equal to 1,300 kilonewtons. Use LRFD, threads excluded from the shear plane. So here we have this connection. As you can see here, we have 3 plates. I have 1 plate, 2, and 3. Each one of them is taking 2/3 of PU. In here, I have 2 plates. Each one of them is taking PU. And I have the bolts penetrated through those plates, and they are creating this connection. So again, it is asking us to determine the number of bolts that we need for satisfying or carrying the PU values shown in here. Now, what would you do in this case? I would like to calculate the force on each shearing plane. Now, if you look in this problem, so is everything. If you look at this problem, actually, you will find that each bolt is actually having not one shearing plane. However, you have one shearing plane in here, second one, third one, and fourth one. So each bolt have 4 shearing planes as shown in yellow. So what I'm going to do is that I will cut my bolt into pieces. Here I have shearing plane number 1, shearing plane number 2, this is 3, and this is 4. This is of course the first one. And I would like to calculate the shearing force on each plane. So from the equations of equilibrium, first of all, let's erase everything. So from the equations of equilibrium, the summation of forces must be equal to 0, of course. Sorry about this. So the summation of forces should be equal to 0. And based on the bolts that I have, okay, I took one bolt. Notice that I have applied force 2/3 pu. I'm getting it from the question because here I had 2.3 pu. So I'm substituting all the forces, of course. Those are given in the problem. Now I would like to find the force on each shear plane. So if we consider the first part in here, if you had 2.2/3 pu applied in this direction, what force should you have on shearing plane in order to satisfy the equilibrium? Of course, it would be the same value, but opposite in direction. Therefore, this would be 866.6 kilonewtons. Now, this shear force would be opposite in direction when you consider the other piece. So it would be opposite in direction, however, the same value, 866 kilonewtons. Now, considering the second piece shown in here, I have 866 and I have 1,300 kilonewtons. What do I need for equilibrium? I need 433 pointing toward the right-hand side. And considering the third piece, again, I will have the same force, however, opposite in direction, 433. Now, if this is 433 and this force applied in here is 866, what do I need for equilibrium? I need, again, another force equal to 433.3 kilonewtons. Now take this force and change its direction for the other piece you have. So in here I have it 433 again. Now this time I have the force on this piece equal to 1,300 kilonewtons. So what force do I need for equilibrium? 866. 866 lastly will be opposite in direction for this part. And here, as you can see, 866 minus 866, 0. So you're all good. Now, considering all the planes you have, what is the maximum value you observe? What is the maximum shearing force you have in here? Now, if we compare, we have 866 in here and here 866. So it doesn't matter which one you choose because obviously I just need what is the maximum value of shearing force. So I'll proceed and consider that the maximum shear force on a plane of bolt is 2/3 pu, which is 866 kilonewtons. Now, from this information, I would like to calculate, okay, before proceeding with this, I would like to calculate actually, okay, first of all, the area of one bolt, AB, is going to be equal to 452 based on the diameter that is given to me or the size of each bolt. Now, also, I would like to consider the shearing stress or the shearing capacity of one bolt. And since the threads are excluded as specified in the problem, therefore, I'm saying 0.625 multiplied by 0.9 multiplied by F ultimate. Since we have grade 8.8, of course, F ultimate would be equal to 8 multiplied by 100, therefore 800. Now from there, FMV is equal to 450 megapascal. Now from there, I can calculate Rn. Rn would be equal to 450. That's FNV multiplied by the area of bolt divided by 1,000 to convert from newtons to kilonewtons. And you get the capacity equal to 203.57 kilonewtons. Now multiplied by 0.75 to factor it according to LRFD, and you have the capacity of one bolt to be equal 152.67 kilonewtons. Now, in order to calculate the number of bolts you need to carry the loads, as I told you before, the maximum force on a shearing plane is 866 kilonewtons. Therefore, I'm dividing the applied force 866 divided by shearing capacity of one bolt, 152.67. Now from here, you get the number of bolts required is equal to 5.67. And of course, you cannot take 5.67 bolts, therefore you take 6 bolts. Now moving on to the third problem. In this problem, it says determine the number of M24 grade 10.9 bolts required to develop full yielding capacity of the UPN members. S275 steel with Fy 275 megapascal and Fu is 430 megapascal. Use LRFD provisions, consider threads excluded from shear plane, and consider 2 rows of bolts in the longitudinal direction. So as you can see here, we have the bolts located just to show us the direction. However, we are supposed to determine the number of M24 grade 10.9 bolts. So it doesn't mean that we actually have 6 bolts. This is just for illustration. Now, we have UPN 300s, 2 of them, and we have a gusset plate, thick plate of 25 millimeters. And UPN 300, we can get its information from the section tables. So we are all set to go. Now, before continuing, we have to actually consider important part in this problem. It says, what is the number of M24 grade 10.9 bolts required to develop full yielding capacity of the UPN 300 members? So you need bolts that are actually going to be stronger than the UPN 300s that you have. Now, based on this information, I will say that the number of bolts multiplied by the capacity of one bolt should be bigger than or equal to the capacity of 2 UPN sections. So in calculating the capacity of the sections, since we have UPN 300, I will multiply 275, that's Fy for the planes, multiplied by the area for UPN 300. However, since I have 2 UPN sections, so I will multiply the area by 2. And I will divide by 1,000 to convert everything from newtons to kilonewtons. Now from here, this is like calculating the gross yielding capacity of the plates. So from here, you get the capacity of the gross yield capacity of the members in tension to be equal to 3,234 kilonewtons. Now I need my bolts to be stronger than the sections that we have. So in order to do that, I would like to calculate the shearing capacity of each bolt. Now, since we are given the size of the bolts and the information such as the threads inclusion or not, so since the threads are excluded in the problem, I will calculate based on 0.625 by 0.9 multiplied by 1,000. Be careful, this 1,000 is coming from grade 10.9 as given in the problem. So since it says 10.9, F ultimate would be equal to 10 multiplied by 100. Therefore, you get 1000. And then I'm multiplying by the area of one bolt. And lastly, I'm multiplying by 2. Why is that? Because you have 2 shearing planes. Now, as you can see, each bolt is actually under 2 shearing planes as shown in yellow. So we have double shear. Because we have double shear, I'm multiplying by 2. Therefore, the capacity of one bolt would be equal to 508.93 kilonewtons. Now, I would like to calculate the bearing of outer bolts based on this equation. So in order to do that, I will go back to my problem in here. As you can see, the bearing of the outer bolts here, this bolt is outer for the thick plate. And those bolts are outer for the UPN 300. And notice that the distance is equal to 50 in here and 50 in there. So in calculating LC, when you calculate from the outer edge to here and the outer edge to there, those two LC values will be equal to each other's. However, in determining which one are you going to be based on working on, you have to consider the thickness of the connections. So either you will be using the thickness of UPNs you have or the thickness of the plate. So as I was saying, in calculating LC value, it would be 50 minus 14, that's half hole diameter, 28 divided by 2, and multiplied by the thickness. What thickness? Now, in the problem, I have the thickness of the gusset plate in between them is 25 millimeters, as shown in here. However, the UPN has a web thickness of 10 millimeters each. So the summation of 10 plus 10, of course, 20 is less than 25. So I'm saying that the thickness in here I'm going to use is 20 because it is more critical. And lastly, I'm multiplying 430 by, that's 430, that's the F ultimate of UPNs that I have, and divided by 1,000 to convert from newtons to kilonewtons. Now from here, I get the capacity for the bolts or the bearing to be equal to 371.52 kilonewtons. Now I continue and I calculate the bearing of inner bolts. Now this time I have 2.4 multiplied by the diameter of each bolt, 24, multiplied by 20, again 20 because I'm considering the least thickness, and multiplied by F ultimate 430 and divided by 1,000 to convert from newtons to kilonewtons. From here, you get the capacity based on the bearing of inner bolts to be equal to 495.36 kilonewtons. Now, as you can see here, I have 3 values. And the least value that I have is the bearing of outer bolts. Now, it is 371.52 kilonewtons. And in determination of the number of bolts required, I would divide the capacity of the planes are in plane 3,234 and divided by the capacity of one bolt, 371.52. From there, you get the number of bolts required to be equal 8.7 bolts. And of course, since we need 2 rows of bolts, I will take 10 bolts. I will take an even number. So since we have 2 rows, that must be the same in number. Here and there, I will take 5 in top and 5 in bottom.
Okay. Now coming to the next problem we have in the problem set. So now continuing with the problem number 4, we have to determine the maximum value of PU permitted. We have to use LR of D. So the maximum PU that's shown here is shown here as well. And we have to consider that we have S275 steel for the plates that are connected. And we have the standard holes. We have M20 bolts, grades 8.8, threads excluded from the shearing plane. Now we have all this information, and we have to basically find what is the maximum PU that is allowable to be applied without causing a failure of our connection. So first thing first, we have to understand the forces on our bolts. We have to find the forces on each of the bolts, one of the bolts that we have in here. Now, if you think about it, what would be the effect of PU on all of the bolts that I have in here? Now, first of all, since we have a PU, there will be a shear force in the Y direction. So if you say that this is your Y direction, and here you have your X direction axis, here you have a shear force that is distributed over all the bolts. So I denote it with VIY dash. That dash means that the shear force is directly coming from PU. Okay. Now ask yourself, do I have any force that causes an effect in the X direction directly? I don't have any kind of force like this. So my VIX dash would be equal to 0. Now, if we consider other kind of effects by the force PU, we find that it might cause a torsion on the bolts. So since you have a distance between this force and the center of the group of bolts, now before we get into that, let me talk about the center of the bolts. Here we have how many bolts? 1, 2, 3, 4, 5. We have 5 bolts in here, and the center of the group of bolts is obviously located in here. And that's the center exactly. Would be located right here at this bolt in here. So if we consider the applied force PU, we realize that there is a distance 300 millimeters to the center of the group of bolts. Therefore, there will be a torsional force. This torsional force would cause a rotation in this direction, counterclockwise rotation. Now, that rotation would cause a shear force in the X direction, as shown in the blue arrows. So I denoted with VIX dash dash because it's coming from the torsional force caused by PU. Now I have the torsional force or the shear force would be the maximum at the bolt that is very far away from the center of the group of bolts. That's why here you see big arrow, and it decreases as you get closer to the center of the group of bolts. And it changes direction as it causes rotation. Now, since we have understood the forces on our bolts, we can start considering writing them down. So as I said before, VIX dash is 0 since I don't have any force that is in the X direction. When we consider VIY dash, that is the direct shear force from PU, that's my PU, and it would be divided by 5 since I want to find the shear force on each bolt. So I divided by 5 bolts. And from here, you get 0.2 PU or P ultimate. Okay, we have to consider also the VIX double dash. How would you find it? First of all, calculate the torsion. So the torsion would be equal to P ultimate multiplied by the distance between the force and the center of the group of bolts, where, as I said before, the center is located right here. So I multiply by 300, and that would be my torsion. Now, besides that, I need one more thing. I need to find the summation of R or the distances of each bolt, the summation squared. So what's that? It's basically, you have to think about, let me first of all erase everything. Okay, so as I was saying that my center of the centroid for all the bolts, the centroid for the group of bolts is here. I have to consider the distance from the X-axis to this bolt in here. So So that's the distance between this bolt, for example, to the centroid of the group of bolts. What's that distance? It's given to us as 75 millimeters. As you can see here, I have one bolt at top and another bolt at the bottom over here. So I have two bolts. Therefore, I say 2 multiplied by 75 squared. Okay, now I have to consider also other 2 bolts that are far away. That bolt over there, that's the last bolt. And I have another bolt over here. They have both the same distance to the centroid of a group of bolts, which is 150 millimeters. So 150 millimeters for the very far away bolt. That's why I multiply 2, since I have 2 bolts, this one and that one at top, by the distance squared, 150 squared. And if you do the summation, you get Ri squared equal to 56,250 millimeters squared. Now, what that would benefit me, it is sort of like you can think about it as a moment of inertia. As the bolts, let's say that this bolt is very far away, located somewhere there, of course, this would result in a very high increase in the R value, which would make the connection resisting more. How is that? We will see when we calculate VIX double dash. So VIX double dash is the shear force caused by the torsional force. In here, I have 300 PU, that's the torsion I found, multiplied by 150. 150 is the distance between the x-axis and the very far away bolt. The very far away bolt is at 150 millimeters. That is the one that has a maximum shear force in the x direction. And that is divided by the summation square of R, the distances of each bolt. And that is 56,250. Now, if this value, as I was saying, that was very big because the bolts were far away from the centroid, this value would be very big. Therefore, VIX double dash would be small. So well, that's one thing to notice. Okay, so in here, as you can see, that's my equation. This is like T multiplied by C, you can say, divided by R. But this R is squared. Okay, now we have everything set in my equation. And I get VIX double dash equal to 0.8 PU. So now I have VIX double dash found, I have VIY dash, and I have VIX dash all found. What else I'm missing? I am missing the VIY double dash. That one is equal to 0 since there is no effect in the y direction from the torsional force. Therefore, VIY is equal to 0 double dash. Now I have all the forces in here found. I will find the maximum shear force that is applied on one bolt. And you can do that by saying VI, that's the shear force or the magnitude of the shear force, square root. Under that square root, you have, let me write it down, VIX dash plus VIX double dash all squared plus VIY dash and plus VIY double dash and squared, and put them under square root. Now, as you can see here, VIX dash is equal to 0. VIX double dash is equal to 0.8 PU, as shown in here. So I substitute it in my equation. And all squared plus VIY dash is equal to 0.2 PU. I substitute it in here. And I don't have the other one, that's 0. I have my equation ready. And therefore, the maximum shear force that is applied on one bolt is equal to 0.825 PU. Now I find it in terms of PU. Now, in order to find what is the maximum load that I can apply, I will go now and find the capacity of each bolt. Since I found the shear force on each bolt, I have to find the capacity of each bolt. So in order to do that, the shearing capacity of each bolt to be calculated first, 0.75, that's my phi, multiplied by 0.625 by 0.9, threads excluded, multiplied by 800 if ultimate for the bolt, and 314 divided by 1,000, that's the area of my, or the area of one bolt. Now from here, the shearing capacity of each bolt would be equal to 106 kilonewtons. Okay. Now we have to decide the capacity not from here, but we have to consider also that I might face a tear out or I might face excessive deformation. So I will consider again the bearing of outer bolts, for instance. So in here, you have to choose LC or a clear distance. Now, if we consider this bolt, for instance, at the far end, this one or the one at the bottom, here you have, for example, the distance 60. You have a 60 in here. And instead of the tear out to be outside, it might happen to the bolt to the next place, the one above it. So as you can see here, I can find LC, and another LC in here. Now, when you see, when you check everything, you can realize that actually these two would be equal to each other. So you can say LC1 and LC2 are equal to each other. That's 60 and that one is 60. What about this one? This one is 75. That one would be different. Now, if we calculate each LC and pick the lowest one of them to plug in my equation, I find that the minimum would be LC1 or LC2. Both of them are the same. Now I consider the whole size 24 divided by 2, and that's the distance 60. 60 minus 24 divided by 2, that's my LC, clear distance. And as we know, multiplied by 1.2. Now I have to consider a thickness of a plate to be multiplied with. So in here I say 15. Now when you take a look, here you have this plate has a 15 millimeters thickness, and that plate has a 20 millimeters thickness. So which one is more critical? Obviously, the one with 15 millimeters thickness. So that's why I choose this one, and I multiply by F ultimate of that plate, 430. Now from here, the bearing of outer bolts would be 278.64 kilonewtons. One more thing, I have to consider that I might have excessive deformations. So I would consider now 0.75, that's my phi. 2.4 multiplied by 20. 20 is the diameter of one bolt. And I will consider the thickness of a plate, the lowest thickness, 15 millimeters, multiplied by F ultimate. And from here, I get another capacity equal to 232.2 kilonewtons. Now I have three capacities. Which one is the lowest? The lowest is this one, 106 kilonewtons. Now, since I have the capacity of one bolt and I have the applied or the maximum shear force on a bolt, I have to satisfy this condition. This condition says that the capacity of the bolts should be bigger than VI. VI, we have calculated it in here. So that's my VI, 0.825. I want my capacity to be bigger than this value. Oh, it's not picking. Okay. So that's my condition in here, and I start substituting. Now, we said that VI is equal to 0.825 PU, and I have phi Rn. Phi Rn, I have already calculated it in here, 106 kilonewtons. So substitute everything in order to find PU. So PU is equal to phi Rn divided by 0.825, and from here you get that the maximum allowable load to be applied is 128.6 kilonewtons. Do we have any questions? Okay, so we can move to the other problem. Now, in problem number 5, we have to determine the maximum value of PU permitted use LRFD. Let's use LRFD. And similar to the previous problem, now we have PU in here, but we have different type of connection. As we can see, these bolts are distributed as shown in here. We are also given that we have a standard hose M22, that's the size, the grade, and threads are excluded from the shearing plane. Now, that's the problem that I have. And first thing I would like to do is to understand the forces on each of the bolts. So before that, I like to find the centroid of the group of bolts. So as you saw, I have 9 bolts. The centroid would be falling in between. In here, these 4 bolts, these 6 bolts, and the 6 bolts at the bottom, it would be in between. That's my x-axis. And the y-axis would fall in the middle right here. So I don't know how to really explain this because it's very logical and very obvious. But anyway, that's the centroid of the whole group of the bolts. Since I have the centroid, I will consider now the forces. So since I have a PU that is applied over here, I would have a shear force in the y direction, which is shown as in here in the yellow arrows. So that would be like my VI y dash. And also, I don't have any force in the x direction, so my VI x dash is equal to 0. If I consider other kind of forces, this PU would cause a torsional force on the group of bolts. So there will be a rotation like this. It would be clockwise rotation. So that rotation would cause another kind of shear force as shown in the blue arrows. So here I show the blue arrows at the corner bolts. Of course, there will be other shear force at the other bolts, but the ones at the outer edge or at the corner are facing the biggest shear force. So that's why I'm focusing at these ones, the very far away ones, from my centroid of all the group bolts. Now I have, as you can see, I have this arrow. It means that I have a shear force in the y direction and I would have a shear force in the x direction. Now to get this more clear, let's write down the forces that we have. So first of all, VIY dash and the yellow arrows would be basically PU divided by the number of bolts. PU divided by 12. And from here, it would be 0.0833 PU. Now, if I consider the one in the x direction, the shear force in the x direction, it would be 0, since I don't have any externally applied force in the x direction. If I check the other forces, VIX and VIY, VIY is here, that would be double dash, that one, VIYX double dash. Before getting into that, I have to consider the torsional force. So how would you calculate it? T is equal to PU multiplied by the distance between the force and the centroid of the group of bolts. So the centroid is 150 millimeters far away from this edge, plus 500 millimeters to the force. That's why it's 650. And multiplied by P. So that's your torsion. Now we have to calculate R I square, the summation. So in here, okay, I have to clear my screen before getting into that. Now in here, for example, let's see these bolts from the x-axis. I will calculate from the x-axis initially. So I have these bolts. I have these bolts. So if you take a look, I have 3 bolts that are located at 50 millimeters far away from the center of the group. So that's 100, half of it would be 50. And you have 6 bolts, 1, 2, 3, and at the bottom as well. Therefore, 6 multiplied by 50 squared. Okay, what else I have? I have this group of bolts and this line over here, and at the bottom, I have to consider that distance as well. So this distance would be 150. 100 plus 50, that's 150 over here, and there is another 150 there. So 150 squared multiplied by how many bolts you have far away at this distance. I have 6 bolts. So 6 multiplied by 150 squared. Now I have to consider about the y-axis since I consider about the x-axis. So your y-axis is located right here in the middle. So the distance between the y-axis and the bolts located at the center is 0. So I'm excluding them already. And if I include the distance between this bolt and the center in here, and also these ones, the distance from here to there, it would be 75. This was 75, this one 75. So now, as you can see, I have 4 bolts and 4 bolts over there at the same distance, 75. So I say the summation of all the bolts that are far away, 75 millimeters squared. And here you have found the summation of Ri squared. You sum them up, you get 195,000 millimeters squared. Now I'm ready to find the Vix dash and Vix or Viy double dash. So how would I calculate Viy double dash? This is my torsion, 650 multiplied by Pu. And then I have, this is the summation of the distances of all the bolts squared, 195,000, multiplied by 75. What's that 75? It's the distance between the y-axis and the very far away bolt. So the very far away bolt is 75 millimeters. So that's the distance between the y-axis and the most far away bolt, 75. I substitute everything and I get Viy double dash equal to 0.25 Pu. Okay, what about Vix double dash? Since this arrow is inclined in such a way that it would give components in the x and y direction, I also have Vix double dash. So that's again my torsion, 650 multiplied by Pu, divided by 195,000, and multiplied by 150. Why is it 150? Because I'm considering now the distance between the x-axis and the very far away bolt from the x-axis, which is 150 millimeters. Substitute everything and you would get Vix double dash 0.5 Pu. Now I have everything set. I have these ones ready, those ones as well. I can find the magnitude of the shear force in a bolt. So the magnitude would be, as we discussed before, the summation of the ones on the x squared and the summation of the ones on the y squared. So first, 0 is coming from here. I have 0.5 Pu that is coming from here, squared, plus 0.0833 Pu, which is this one, and I have 0.25 Pu, which is that one, all squared. Under square root, you get Vi, or the magnitude of the shear force on a bolt, would be 0.6 Pu. Now from here, I have the shear force on a bolt. I have to find the capacity of my bolts. So first of all, we consider the shearing capacity of each bolt. Again, as we were doing before, the threads are excluded. That's my phi. I have the area of the bolt multiplied by F ultimate 800. From here, the shearing capacity of each bolt would be 128.29 kilonewtons. Now I have to check the bearing of outer bolts. So that's the thing we have to consider in here, LC, the clear distance. As you can see, the distance in between from here to there, 75 minus 26/2, that would give me LC, clear distance, multiplied by the thickness of the plate. Which plate? As you can see, this plate is 20 millimeters and that one is 20, so it doesn't matter which one you pick. So I take 20. And lastly, I have F ultimate over here, 430. Now we substitute everything, we get the bearing of the capacity of outer bolts, 400, almost 80 kilonewtons. Now, if we check for the inner bolts, we consider now the excessive deformation. So that's the diameter of my bolt, 22 millimeters. That's the thickness of the plate, and that's FU or F ultimate of a plate. Substitute everything, and you would get 792 kilonewtons as a capacity. Now, obviously, between all of these three, this one is the minimum, 128.29 shearing capacity of each bolt. So I will proceed with that value, and I want to satisfy this condition in order to find the ultimate load that I can apply PU. Since I have VI and I have phi Rn, there's my equation, 0.6 PU should be less than or equal the capacity of one bolt. And expand this equation, and from here you can find your ultimate load that you can apply, 214 kilonewtons. Okay, do we have any questions here, guys? Okay, I think we can proceed to the, yes.
I have a question.
Sure.
What if the distance between the bottom bolt and the bottom edge of the plate was less than 75? Would we take that distance as a clear distance? I mean, this, how can I show you?
So let me try to understand
this
what
one.
you're saying. Nice. So this is 75, okay. Yeah, so actually
you took this one.
Mm-hmm. That's true.
What if this one was less than 75? Would I take this
That's
clear
good.
distance?
That's good. You would take the smallest clear distance.
Okay.
Because the shearing effect is in the X and the Y direction. So actually that bolt might come out from here, or it might come out from there. Or it might even go to the next bolt. That's the tear out distance that might happen. So you would pick the least clear distance. You're welcome. Any more questions, guys?
Yes, Hojam.
Yes.
Like, what if the thickness of the plates were not the same? Which one should I take?
You would take the least thickness. So for example, in our case, it says 20 millimeters plate, and that one is 20 millimeters. What if this one was 10 millimeters? So that would be your limiting plate. And you would consider the thickness as 10 instead of 20, as we did in the previous questions.
Okay, thank you. But could you go to the previous one to take a picture?
Sorry, what is it?
Can you go to the previous slide to take a picture, please?
I will do that at the end, after I finish all the problems.
Okay.
Can I ask you something?
Sure.
It will be a silly question, but like while we are calculating shearing capacity of each bolt, why didn't we divide by 1,000?
Why we didn't divide by 1,000? Why would you divide by 1,000?
While we are calculating the area, we were dividing by 1,000.
Yeah, I think I did not show that dividing by 1,000 in here. That's because maybe I forgot that. The 1,000 is just for a conversion. Like when you multiply all these numbers, I think you would get 128,290 newtons. So actually, you would divide by 1,000 to get in kilonewtons. It becomes 128.29 kilonewtons. That's why I divide by 1,000. Is that your question?
Yeah, it was my question, and I have one more question, but I can ask you at the end of the section because it was about previous question and again 1,000 issue. So I can ask you at the end of the section if you want.
Sure, no problem. Okay, any more questions related to this, guys? All right, let's proceed to the last problem in here. Okay, give me a second. Okay, now in problem number 6, it says determine the number of M20 grade 8.8 bolts threads excluded from shear plane required at the flange of I shape shown, bearing type connection. And it says do not consider bearing limit state. And also we have to use LR of D, and we're given S355 steel, etc. So in here in this connection, as we can see, we have this HEB 300. We have a plate that is connected 25 millimeters, another plate in here, and we have these bolts. These bolts are shown in red. 2 vertical rows of bolts. So if you look from this direction, what would you see? You would see something like this. Yeah, something like this, and you have your bolts over here. 2 vertical rows of bolts connected. Okay, so we have to determine how many bolts we need. Now, in order to solve this problem, again, I have to consider the effective forces on my bolts. So as you can see here, I have 1,300 kilonewtons applied force. In that direction, 45 degrees. So if you consider that force, divide it into forces, first you realize that you have a shearing force effect on all of your bolts. And I call it VI. Now there is another component of this force in the X direction that would cause a tensile force on my bolts. That tensile force is creating tension on my bolts, where the other force or the other component of the force is creating shear on my bolts. So one of them is tension force, the other one is shear force. That's why I call VI and NI. How would you calculate VI and NI on each bolt? It's basically 1,300 sine 45 in order to get the X component of 1,300. I multiply by sine 45, and I divide by the number of bolts in order to distribute that normal force over all the bolts. So I have 919 divided by number of bolts. That one, I keep it like it is because I don't have the number of bolts yet. So I keep it as a variable. You can call it X, whatever you want. Now we can check the VI, the shear force on each of the bolts. So that one, 1,300 multiplied by cosine 45 to get the component of this force, shown in yellow, and divided by the number of bolts again. So that one is again 919 divided by the number of bolts. Now I have the forces on my bolts, NI and VI. What do I have to find else? I have to find the nominal shear stress. Again, going back to the table J3.2 as a reminder. I'm getting back to this table. Now, one thing I want to mention, in the previous problems, we had all the forces causing shear effect. In this problem, we don't have only shear effect, but we have a tension effect as well, as shown in here. So we will be using different equations than we used before. But before we get into that, I will calculate necessary things I need for my equation. So first thing, I have to consider the nominal shear stress from table J3.2, FNV. FNV, since the threads are included, sorry, they are excluded, I'm considering FNV 0.563 FU. So multiply that and you get 450 megapascal. Now I need one more thing. I need the nominal tensile stress, since I have tensile force, and that is called FNT. You go back again to the table, and FNT is actually shown in the first column. That's your FNT. How would you calculate that? Similar to this one, threads excluded, and it would be 0.75 F ultimate. So 0.75 multiplied by 800 would give me 600 megapascal. What else do I need? I need the required shear stress or the shear stress acting on a bolt. So FRV would be dividing the normal force in I, the required shear stress is actually VI divided by the area of one bolt multiplied by the number of bolts. So in here, if you do that, you would get like the unit newtons per millimeter squared or megapascal. So that's the stress, required shear stress. So I have everything fit in here. I have found my FRV, my FNT, my FMV. I can proceed to use or satisfy a condition. What does this condition say? It says that I need my capacity of bolts to be higher than the tensile force that is applied. So in order to find the capacity or in order to satisfy this condition, when you have a tension force, this equation becomes slightly different. Instead of using AB multiplied by FNV, it becomes multiplied by FNT dash. And here I have NI. So expand this equation, it becomes like this. 0.75, that's my phi. AB is the area of the bolt. FNT dash has this equation to find it. And you have NI. So as I was saying before, this capacity should be bigger than NI, the tensile force that is applied on the bolts. Now, previously we have found FNT and we have found FRV and FNV. I can substitute everything in my equation in here. So that's the area of the bolt. I divide by 1,000 for conversion to kilonewtons. What else I have? So I substitute now 600 instead of FNT as I found before, the nominal tensile stress. I have also FNV, 450 as we found. FRV, that's like the stress in here, and divided and equal to NI divided by the number of bolts, since the tensile force will be distributed over all these bolts. Now, as you can see, the only unknown I have in my equation is that hashtag, which is the number of bolts. So if you solve for that number, okay, before that, here we are showing that this part is FNT dash, this one is NI, normal force, this one is the whole capacity of one bolt. Now, if we solve this equation, we find that the number of bolts required to satisfy our needs to hold that 1,300 kilonewton safely is 11.67 bolts. And obviously, since we are using two vertical rows, I need the even number. So I would be using 12 bolts. Now, since you picked 12 bolts, I have to do one more check before I proceed. I have to check that, okay, here I'm showing the distribution of my 12 bolts. Okay, now, as I was saying before, I have to check one more condition. After picking the number of bolts, I have to check FNT dash should be less than FNT. So if we expand our equation, here I have FNT dash, and here I have my FNT, which I already calculated previously, 600. So I start substituting everything in the equation, and here I substitute the number of bolts, 12. This is the area of the bolt, this is FNV, that's the whole thing of FRV. So basically substituting everything in this equation and check if it's less than 600 or not. Now, when we substitute, we realize that this would give me 346.4, which is less than or equal than 600 kilonewtons, and that is good. If it was not the case, try increasing the number of bolts in order to satisfy this condition. And that's the end of our problem session. Do we have any questions related to this problem?
Hocam if there is 10.67, for example, bolts required, so can I say 11 bolts I will use? So I
No, you
can
would
take
say
11.
even if it's say 10.67, you would pick 12 bolts because we need 2 vertical rows of bolts. If you had, you're welcome. But that's a good question. I want to explain further. If you had, for example, here 5 bolts and here 6 bolts, let's say here we have 6 bolts, here we have 5 bolts. Since the bolts are not evenly distributed, that might create stress distribution issues. And we might have some complications. That's why we want to avoid that, and we want them to be evenly distributed. Okay, any more questions, guys?
Not on this question, but in question 3, I have one question.
Okay, which question exactly?
Question 3.
Question number 3. Let's go
Yes.
to question number 3. Okay, so that's question number 3.
Yes, hocam, exactly here. Like I was asking 1,000 question like 10 minutes ago. In this one, while we are finding Rn bolt, we multiplied with 1,000 and then divided again 1,000.
Yeah,
It was,
you confused. I think you confused with this 1,000, right?
Yeah, exactly. What's that stand for? That 1,000.
That 1,000 is actually if ultimate. Usually we say 800,
Oh,
but
okay,
because
okay.
we are given in the problem that the grade is 10.9. The grade is 10.9, so if ultimate would be 10 multiplied by 100, that would be 1,000.
Okay, hocam, I get it. Thank you.
You're welcome. Any more questions, guys? All right, so there is one more guy who asked me to take photos for the slides. Are you still here?
Yes, I just need for question 5.
You just need question number 5.
Yes, and 6, I think.